C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 9. Let's discuss Chapter 9, Streaming Inference to the Console. Let's discuss theoretical foundations. The core challenge in making a local large language model, LLM, feel alive is overcoming the latency of the generation process. When a user sends a prompt to a local model running via ONNX Runtime, the model does not simply return a finished paragraph. Instead, it performs a massive matrix multiplication operation to predict the very next token, returns that token, feeds it back into itself as input for the next step, and repeats this cycle hundreds of times. If we were to wait for this entire cycle to complete before showing any output to the user, the application would appear frozen for seconds or even minutes. This creates a jarring, unnatural user experience. To solve this, we must treat the LLM not as a static function that returns a result, but as a continuous source of data, a stream. In C#, the premier mechanism for handling asynchronous data streams is the iasync enumerable T interface. This interface allows us to yield results as they become available, creating a bridge between the heavy computational world of ONNX Runtime and the responsive, interactive world of the user interface. Now, let's explore the assembly line analogy. Imagine a highly skilled chef, the LLM, preparing a complex, multi-course meal, the generated text. The chef works in a kitchen isolated from the dining room, the user interface. 1. The synchronous approach, the all-at-once meal. The waiter takes the order and waits at the kitchen door. The chef cooks the entire 7-course meal, plates it, and only then hands it to the waiter. The waiter walks out and serves the entire meal at once. The diner is left waiting for a very long time with an empty table, unsure if anything is happening. 2. The asynchronous streaming approach, the course-by-course meal. The waiter takes the order and immediately goes to the kitchen door. As soon as the chef finishes the appetizer, the first few tokens, the waiter takes it and serves it to the diner. While the diner is enjoying the appetizer, the chef is already working on the soup. The waiter keeps checking back, taking each dish the moment it's ready. The diner gets immediate feedback, the meal feels engaging, and the kitchen's workflow is continuous and efficient. In this analogy, the chef is the ONNX Runtime inference session. The kitchen is the background processing thread. The waiter is the iasync enumerable pipeline. The dishes are the individual tokens. The diner is the console or UI. Our goal is to build the waiter and the kitchen workflow in C# so that the diner never has to wait for the entire meal to be finished. Let's discuss the foundation, iasync enumerable T. Introduced in C# 8.0, iasync enumerable T is the asynchronous counterpart to IEnumerable T. While IEnumerable T represents a sequence of values that can be iterated over synchronously, iasync enumerable T represents a sequence that can be iterated over asynchronously. The key method here is await for each. This language construct allows a consumer to pull items from a producer as they become available, without blocking the calling thread. Here, we're defining a method called consumeStreamAsync. Notice the async keyword, which tells us this method can perform asynchronous operations. We're also accepting an iasync enumerable string as an argument, which is crucial for handling streams of data that arrive over time, like tokens from an LLM. This design pattern allows us to process data as it becomes available, rather than waiting for the entire stream to complete. This is a fundamental concept for responsive applications, especially with real-time data or long-running operations. Without iasync enumerable, we would often have to buffer the entire output, which could consume significant memory and introduce unacceptable latency, especially for large language model outputs. This is crucial for AI applications because the producer, the inference loop, is subject to variable latency. Some tokens are generated quickly, common words, while others take longer, rare or complex words. iasync enumerable respects this natural cadence. Now, let's talk about the technical workflow, from tensor to text. The process of generating a stream of text involves a tight loop that bridges the high-level C# logic with the low-level numerical operations of the ONNX model. This loop is the engine of our streaming pipeline. Turning our attention to 1. The inference loop. The loop's primary job is to repeatedly call the ONNX Runtime inference session, run, method. However, run is a stateless operation. It takes an input tensor and produces an output tensor. It has no memory of what was generated in the previous step. To give the model memory, we must maintain the state ourselves. This is the inference loop. 1. Tokenize the prompt, convert the initial user prompt into a list of token IDs. 2. Initial run, feed these token IDs into the model to get the first set of logits, raw predictions. 3. Process logits, convert the logits into a probability distribution and select the most likely token ID. 4. Yield token, convert the token ID back to text and yield it to the stream. 5. Update state, append the newly generated token ID to our list of input tokens. 6. Repeat, go back to step 2, using the updated list of tokens as the new input. This loop is the heart of the generation process. It must be implemented carefully to ensure it can be paused and resumed as we stream tokens. Let's discuss 2. Tensor manipulation and post-processing. When inference session, run, returns, it gives us a named value object containing a tensor float. This tensor represents the logits, a raw, unnormalized score for every single token in the model's vocabulary. To turn these logits into a meaningful token, we perform 2 critical steps: softmax. Conceptual, we convert the raw logits into probabilities. A higher logit score becomes a higher probability. This is often handled by the model itself, but conceptually, we are looking for the token with the highest score. Argmax, selection, we scan the tensor to find the index of the highest value. This index is the ID of the next token. Detokenization, we use a vocabulary mapping, loaded from a tokenizer.json or similar file, which we built in a previous chapter, to look up the string representation of this token ID. This process transforms a multidimensional array of floating point numbers into a single, human-readable character or word piece. This diagram illustrates the architectural flow where a multidimensional array of floating point numbers is processed by an ONNX engine and streamed through a pipeline to a UI consumer, transforming complex data into a single, human-readable character or word piece. Turning our attention to why this matters for Edge AI. This architectural pattern is not just a nice-to-have, it is fundamental to the viability of local AI. 1. Responsiveness. By streaming, we can display the first token within milliseconds of the request, even if the full response takes 30 seconds. This immediate feedback psychologically reduces the perceived wait time. 2. Memory efficiency. Instead of storing the entire generated response in memory before displaying it, we process and display it token by token. For very long generations, this is critical. 3. Cancellation. Because the generation happens inside an async iterator, it is naturally interruptible. A user can press a stop button, and we can simply cancel the await for each loop. The cancellation token can be passed down into the inference loop, allowing it to gracefully terminate the inference session, run, call if it's in the middle of a long computation. This is impossible with a synchronous, blocking call. Now, let's talk about the role of previous concepts. This chapter builds directly upon the foundation laid in Book 8, the ONNX pipeline. Specifically, we rely on the inference session object created there. The inference session is the loaded model, the brain, that we will now learn to converse with in a real-time dialogue. Furthermore, the tokenization logic, the mapping of strings to token IDs, is the inverse of the detokenization we will perform here. The vocabulary map created during tokenization is essential for converting the generated token IDs back into text that the user can read. Without that pre-processing step, the output of this chapter would be nothing but a stream of meaningless integers. Now, let's explore basic code example. Here is a basic code example demonstrating asynchronous streaming of LLM tokens to the console using C# and ONNX Runtime. Moving on to the problem, the waiting cursor. Imagine you are building a local chat application. When you ask a question, the AI takes a few seconds to generate a response. If you wait for the entire response to finish processing before displaying anything, the user sees a frozen screen or a spinning wheel. This feels slow and unresponsive. The goal is to mimic human typing. As soon as the AI generates a word, or a token, we want it to appear on the screen immediately. This requires streaming inference. Now, let's talk about the code example. This example simulates the core logic of streaming tokens. It uses a mock inference session to represent the ONNX model execution, focusing on the async enumerable pipeline that handles the asynchronous generation and display. We begin by importing necessary namespaces. These using directives bring in functionalities from the .NET framework that our application will rely on. For instance, system, collections, generic is crucial for working with collections like lists, system, link provides powerful query capabilities, and system, threading, tasks is fundamental for asynchronous programming, which is at the heart of our streaming LLM simulation. System, runtime.compiler services is specifically needed here for the enumerator cancellation attribute, which helps the C# compiler understand how to propagate cancellation tokens into asynchronous enumerators, ensuring our streaming operations can be gracefully stopped. Here, we declare our main namespace Edge AI streaming demo, which acts as a container for all related code, preventing naming conflicts and organizing our project. Inside this, we define the mock inference session class. Notice the comment block from lines 10 to 13, this explicitly states that this section is a mock infrastructure. This is a crucial design choice. Instead of directly integrating with the complex Microsoft.ml.ONNX Runtime.Inference session for this demonstration, we create a simplified stand-in. This allows us to focus on the streaming logic without getting bogged down in the intricacies of ONNX Runtime setup, model loading, and tensor manipulation. It isolates the core concept of token generation and streaming. The mock inference session class implements iDisposable. This is a best practice for classes that manage unmanaged resources or, in a real scenario, potentially large managed resources like an ONNX runtime session. Implementing iDisposable allows us to define a dispose method, seen later at line 60, that will be called to clean up resources, preventing memory leaks. The constructor at lines 20 to 24 initializes a_mock vocabulary. This small array of strings acts as our language model's vocabulary. In a real LLM, this would be a massive, learned vocabulary, but for our mock, it's sufficient to demonstrate tokenization and decoding. The choice of a read-only field for_mock vocabulary ensures that once the vocabulary is set during object creation, it cannot be accidentally modified later, promoting data integrity. The runAsync method, lines 29 to 51, is the core of our mock inference. It simulates the run method of a real ONNX runtime inference session. This method is declared as async task int, indicating it's an asynchronous operation that will eventually return an integer, representing the ID of the next predicted token. The cancellation token parameter is vital for responsive applications. It allows external callers to signal that they no longer need the result of the operation, enabling the method to stop processing early and release resources. At line 31, we simulate inference latency using task delay. This is a critical simulation detail. LLMs, even on local hardware, take time to process each token. By introducing this artificial delay, between 100 milliseconds and 300 milliseconds, we accurately represent the real-world performance characteristics and demonstrate why asynchronous streaming is so important for user experience. Within runAsync, the switch expression, lines 36 to 48, provides a simple, deterministic way to generate a sequence of token IDs. This is purely for demonstration purposes to produce a readable output like, "Hello world. How are you?" In a real LLM, this logic would be replaced by complex neural network computations that take the input token, and often the entire input sequence, and predict the probability distribution over the entire vocabulary for the next token. The model would then typically sample from this distribution or pick the most probable token. Our mock simplifies this to a direct mapping, allowing us to focus on the streaming mechanism rather than the LLM's internal workings. The return value of -1 at line 48 signifies the end of the sequence, a common pattern in LLM outputs to indicate when the model has finished generating text. The token ID to string method, lines 53 to 58, serves as our tokenizer/detokenizer. Given a token ID, it looks up the corresponding string in our _mock vocabulary. In a real LLM pipeline, this would involve a more sophisticated tokenizer, like byte pair encoding or word piece, that handles subword units, special tokens, and mapping between numerical IDs and actual text. For our simulation, a simple array lookup is sufficient. The bounds check at line 56 is a good defensive programming practice, preventing index out-of-range exception if an invalid token ID is passed. Finally, the dispose method at line 60 is a placeholder. In a real inference session, this would contain logic to unload the ONNX model, release GPU memory, or close any native handles, ensuring efficient resource management. The empty implementation here is adequate for our mock, as it doesn't hold any unmanaged resources. Moving on to our core logic, we define the streaming generator class, lines 67 to 108. This class is responsible for orchestrating the text generation process. It holds a reference to our mock inference session, or a real inference session in a production scenario, through its constructor at lines 70 to 74. This is an example of dependency injection. The streaming generator doesn't create the inference session itself, instead, it receives an already initialized one. This design makes the streaming generator more flexible, testable, and decouples it from the specifics of how the inference session is created or configured. We could easily swap mock inference session for a real one without changing streaming generator's logic. The generate stream async method, lines 82 to 107, is the heart of our streaming architecture. Notice its signature, public async iasync enumerable string. This is a powerful C8 feature that allows us to define asynchronous streams. Instead of returning a task list string, which would mean waiting for all tokens to be generated before returning anything, iasync enumerable string allows us to yield return individual tokens as soon as they are available. This is absolutely critical for LLM applications, as it provides a much better user experience by showing text progressively rather than waiting for the entire response. The enumerator cancellation attribute on the cancellation token parameter ensures that the cancellation token is correctly propagated into the asynchronous iterator state machine, allowing the await for each loop consuming this stream to respond to cancellation requests. Inside generate stream async, we initialize current token ID with the prompt token ID. This is analogous to providing the initial input to the LLM. The while, true, loop, line 89, represents the continuous generation process, where the model iteratively predicts the next token. At line 92, we await _session.run async. This is where the actual, mocked, inference happens. The await keyword ensures that the execution of this method pauses until run async completes, but critically, it does not block the calling thread. This allows other tasks to run concurrently, maintaining application responsiveness. After getting the next token ID, we check at line 95 if it's the end of sequence, -1 in our mock. If so, we break out of the loop, signaling the end of generation. Once a next token ID is received and it's not an end-of-sequence token, we immediately convert it to its string representation using _session.tokenID to string at line 99. The most crucial part of the streaming mechanism is at line 102, yield return token text. This line sends the token text back to the caller immediately. The generate stream async method then pauses its execution until the caller requests the next item in the stream. This is the essence of asynchronous streaming. Finally, at line 106, current token ID is updated to next token ID. This forms the autoregressive loop. The newly generated token becomes part of the input context for predicting the next token, mimicking how LLMs generate text token by token, building upon their previous output. Now we move to the consumer part of our application, the program class, lines 114 to 157. This is our console application entry point, where everything is brought together. The main method is declared static async task, indicating it's an asynchronous entry point, which is standard practice for modern C# console applications that perform I/O-bound or CPU-bound asynchronous operations. At line 118, we print an initialization message. Then, at lines 121 to 122, we instantiate our mock inference session and streaming generator. Notice the using var inference session equals new mock inference session. This using declaration ensures that inference session, dispose, will be automatically called when the inference session variable goes out of scope, guaranteeing proper resource cleanup even if exceptions occur. This is a robust way to handle disposable objects. At lines 124 to 125, we create a cancellation token source. This object is critical for managing cancellation in asynchronous operations. It allows us to create cancellation token instances, like CTS token, that can be passed to our asynchronous methods. If CTS cancel is called, all operations observing that token can gracefully stop. This is a fundamental pattern for building responsive and robust applications, allowing users or the system to interrupt long-running tasks. The try block starting at line 127 is essential for handling potential exceptions during the streaming process, ensuring our application doesn't crash unexpectedly and provides informative error messages. This block contains the core consumption of our asynchronous stream. At line 133, await for each var token in generator.generate stream async 0 CTS token is where the magic happens. The await for each construct is specifically designed to consume async enumerable streams. It asynchronously retrieves each token as it becomes available from generate stream async. As soon as a token is yielded, it is immediately written to the console using console write token at line 136. This demonstrates the real-time, token-by-token output characteristic of streaming LLMs. The console out flush at line 139 is an important optimization. In some environments or when output is redirected, console write might buffer output. Explicitly flushing ensures that each token appears on the console without delay, enhancing the perception of real-time generation for the user. After the await for each loop completes, either because the stream finished or was cancelled, we print a completion message. The catch blocks are crucial for robust error handling. The operation cancelled exception at lines 148 to 150 specifically catches cancellations initiated via the cancellation token. This allows us to differentiate between a user-initiated stop and other types of errors. The general exception X catch-all at lines 151 to 154 handles any other unexpected errors that might occur during generation, ensuring that the application provides feedback instead of silently failing. This structured exception handling makes the application more resilient and user-friendly. The entire program class showcases how to effectively consume an async enumerable for a responsive, streaming user experience, which is paramount for interactive AI applications. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 9 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.